Yeah.
Welcome at Eindhoven University of Technology.
Hello everybody, my name is Harald Kloft. I'm the head of the Institute of Structural Design at TU Braunschweig. Together with my colleague Hans Kraus, we like to present our research on the influence of process parameter on the interlayer bond strength of concrete elements additively manufactured by the shotcrete 3D printing technology. At first, I will give a short introduction in our laboratory as well as the SE 3DP technology. Hans Kraus will then present our case studies and discussions on the results, and after his conclusion I will give an outlook to our further research. The heart of our research infrastructure is the so-called Digital Building Fabrication Laboratory, DBFL. Basis on the DBFL is a large-scale machining center from the stone processing industry with a 5-axis CNC portal. The innovation consists in the integration of a second portal with a heavy-duty industrial robot with a total of 9 degrees of freedom, like you can see here. In addition to the structural extension of the machining center, the control integration had to be solved. We decided to integrate the robot control into the numeric control of the machining center. And the cooperative working space is 2.5 meters in height, 5.24 meters in the width, and 10.52 meters in the length, with an accuracy of 0.5 millimeter. The DBFL enables us to process large format components of different materials. With regard to the material concrete, we can manage additive manufactured processes, like you see here, as well as high precision subtractive processes. You can see here. And the special feature of the blend is that both portals can also carry out synchronous processes, like you can see here in the third slide. The results of the investigations presented today are based on a 3D printing process for concrete components developed at the TU Braunschweig in 2016. The special feature is that the concrete matrix is accelerated by adding air shortly before the nozzle exit. It can be said that this acceleration of the material creates a kind of layer by layer compaction. In contrast to the compaction by concrete vibrators, this can of course not be described as homogeneous. And in the following, Hans Kraus will show you whether and how the apparently homogeneous material, like you see here, in the microstructural area can really be described as homogeneous. So I hand over now to Hans Kraus.
Hello everybody, my name is Hans Kraus. I'd like to present you now the case study on the influence of process parameters on the interlayer bond strength of 3D printed concrete elements. And I'd like to start with the influencing factors on interlayer bond strength. First we have adhesion, as you know, at the beginning dominated by rheological properties and later on by setting and hydration mechanisms. And on the other hand, we have interlocking, which is microscopic roughness, dominated by the material properties, and here especially by the particle size distribution, but also by rheology. And of course by the printing process itself. And today we'd like to analyze the influence of process parameters in the case of extrusion and of shotcrete 3D printing. The material we used was spraying mortar available on the market. You see here the mortar composition. It is quite a complex composed material with a lot of chemical mixtures which were contained in pulverized form. Here too, I don't like to go into details. However, we need such a complex material in order to match the rheological requirements for pumping, spraying, extrusion, and for the fast structural buildup after application. As you can see in this diagram, this material we used shows an excellent structural breakdown under shear, and not shown in the diagram, but also evidently it exhibits also a very fast structural build-up after application. Now, the process parameters we used are of course different for the two processes because we found different optimum parameter ranges for the two processes in order to get proper specimens. In case of material spraying, we could manage a higher material mass flow, also a higher robot speed without fracture of the strands in the fresh state. And of course, we have used air pressure of about 2 bars and a nozzle distance in case of shotcrete 3D printing, whereas in case of extrusion, we of course attach the extruder head to the substrate layer. The goal was to achieve comparable layer heights that we indeed roughly achieved. We got 90 millimeters in case of spraying and 20 millimeters in case of extrusion. And finally, due to the different process characteristics, we have different layer width of about 145 and 80 to 90 respectively in case of extrusion. So, and as a consequence, we produce different sample geometries because in case of shotcrete 3D printing, the strand was broad enough to produce linear strands of 1 meter length by moving the nozzle back and forth. In case of extrusion, we had to produce rectangular specimens by moving the extruder head only in one direction, and the edge length you can see here. Here you can see a longitudinal cross section of the main specimens we produced. Every specimen consisted of 10 layers with one main interface between layer number 5 and 6. The reason was that we analyzed different delay times at this main interface of 0 minutes, which is the standard delay time, 15, 16, and 120 minutes. Afterwards, we took prisms to investigate the mechanical performance. On the one hand, we had the main interface contained in the prism HM, horizontal, from the middle. Here, the main interface was allocated into the long axis, parallel to the long axis, whereas in the vertically taken prism, the main interface was allocated perpendicularly to the long axis. And in addition, we had here and here taken prisms with standard interfaces exactly in the middle of the prism. Finally, we also took a drilling course in order to analyze the air void distribution by computer tomography. And we compared the two printing methods to cast and vibrated mortar prisms as a reference. Now here you see some pictures. On the right hand, you see that we indeed succeeded in spraying rectangular strands, which is not really an easy task. And that's why we need a very special material with very special rheology. And we use the same material for extrusion. On the left side, you can see that it may not be perfectly optimized for purpose of extrusion, but however, in the inside, in the middle of the strands, we have a rather homogeneous structure, microstructure, and there we took the prisms from. Now let me first come to results in the fresh state. In extra tests, we tested the penetration resistance on specimens produced by both methods, printing methods. And as you can see here, we calculated from the normal force we measured by the penetrometer the yield stress by the approach of Lutens et al. Given here on the right side. Basically, we have a higher level of yield stress in case of sprayed specimens of about 10 kilopascal as compared to 6 kilopascal in case of extruded specimens. And this may be due, on the one hand, to the higher bulk density, as I will show on the next slide, and on the other hand, due to an assemblage of sand grains in the middle of the sprayed layer, which is typical for spraying processes. We have no clear explanation for the steep increase of yield stress here after 70 minutes in case of shot-treat 3D printing. We are still working on that problem because there is no real reason from the viewpoint of chemical hydration, because hydration really starts only here after 140 minutes significantly. So we are working on that question. But however, we can keep in mind that after those results, the shot-treat 3D printed specimens should be more prone to cold joint formation than the extruded specimens. And now I come to the results of bulk densities. We can see that as compared to the reference specimens here, we have slightly higher or significantly higher bulk densities in case of SC 3DP of about 2 and 9%. And on the right side, we can see that the compressive strength results do well correlate with the bulk density results, as is expected. And here we can also see that there is no significant effect of the main interface or the delay times on compressive strength. It seems to be dominated only by bulk density. This is different for the flexural strength results here on the right diagram as compared to the compressive strength results I showed before. First, we can see a generally different level of strength, with the highest strength for the shotcut 3D printed specimens and the lowest strength for the extruded specimens as compared to the vibrated specimens. And second, we can clearly see a detrimental effect of the main interface and maybe also of delay time. We have not resolved the delay time in this diagram, but if we take a look at the influence of delay time on flexural strength, then we can see some clear effects of the process itself as well as of the delay time. So first, if we take a look at the blue curves, then we can see no clear effect of delay time in both cases. Yeah, you can see a horizontal development of the curves independently whether it was the main interface here, HM, or the standard interface, HT and HB. This seems to have no clear effect if the main interface is allocated parallel to the long axis. If it is allocated perpendicularly to the long axis, then we have, of course, a detrimental effect as expected. And in case of shotcut 3D printing, we have a drop at the beginning at 50 minutes, but for longer delay times, we have no further drop. The results remain rather constant. It's different in case of extrusion. Yeah, here we cannot see a drop at the beginning. This may be due to scattering of results, but later on, the drop in results becomes larger and larger. So, and now I'd like to discuss two main possible reasons for the results we observed. Firstly, I'd like to present you the results on the porosity distribution or air void content distribution over specimen height. We analyzed by computer tomography. For details, please take a look into our paper. And what we can see is that we generally have a lower level of air void content in case of sprayed specimens as compared with extruded specimens. But here in this region, where we have the interface, as well as in this region, we see two characteristic points. First, we see in both cases porosity minimum, which is very distinct, and you see here the evidence from computer tomography in form of false color images. It's very low porosity here in case of shotcut 3D printing and slightly higher but homogeneously distributed porosity in case of extruded specimens. Whereas above the interface we have a zone of higher porosity, and you can see this clearly by the images. So now first we have to keep in mind this strong inhomogeneity, which should have or is expected to have an influence on mechanical properties. And second, we have a difference between shotcut 3D printed and extruded specimens. Evidently, also in case of extrusion, we have a good compaction beneath the interface zone, which may be exhibited by the extruder head compacting the substrate layer when it slides over it. And here we have an even better compaction in case of shotcut 3D printing, which is due to the high kinetic energy of the material. And the sand grains may be penetrating into the substrate. Now I'd like to come to the second main influencing factor, namely the influence of mechanical interlocking exhibited by microscopic roughness of the interface between two layers. And in order to investigate this, we performed extra tests with the same printing methods and the same process parameters, where we strew bright powder on the substrate layer in order to get a better contrast later on in the computer tomography. And afterwards, we applied the second layer. Now, here you can see the results from computer tomography. On the left side, you see the layer or the interface. In case of extruded specimen, you see a very smooth interface as expected. And on the right hand, you see the image of the interface of a shotgrid 3D printed specimen, which is very rough and hence has an increased contact surface, which maybe help mitigate some problems we get with cold joint formation by, for example, fast structure build-up, as shown some slides before. And this may, to a high degree, explain the very good mechanical performance, especially in terms of flexural strength of shotgrid 3D printed specimens. So, and now I already come to the conclusions. As we could show, we have increased bulk densities in both cases, in case of extrusion and in case of shotgrid 3D printing, as compared to cast and fabricated samples. However, shotgrid 3D printing leads to the highest bulk densities. And this, again, leads to the highest compressive strength, which strongly correlate with bulk density. But here we could see no significant effect of layer interface or delay times. We could see such a clear effect of layer interface and delay times in case of flexural strength. And here the shotgrid 3D printed samples showed the highest and best performance as compared to extruded or cast and fabricated samples. And the reasons, therefore, we discussed are on the one hand the increased bulk densities, which is lower porosity, caused by the greater compaction by compressed air, and on the other hand the enhanced interlocking at the interface caused by sand grains penetrating into the substrate. And here also the rheology of the paste phase may be of importance, how deep and how strongly those sand grains penetrate into the substrate. However, in both printing processes, we saw strong microstructural inhomogeneities in the interface zone, and they may be one of the most important reasons for a loss in performance in terms of tensile or flexural strength. And here we should put focus in future research, after my opinion. So now I hand over the word again to Harald to give you an outlook.
So let me give some ideas on our further research. The investigations on shotgrid 3D printing are now integrated in the newly established Collaborative Research Center, TRR277, Additive Manufacturing in Constructions. The two universities, TU Braunschweig and TU Munich, aim to fundamentally investigate additive manufacturing as one of the future manufacturing technologies in constructions. So in total we have 3 areas. Main focus is on the development of new material and process combinations. We have 8 different projects here with different materials, mainly of course dominated by concrete materials, and those investigations are strongly connected to computational and modeling and process control projects, as well as the integration on the interfaces to the design and construction phases. Regarding the further research on cementitious materials integrated here, we focus on material process interactions and optimization. The integration of reinforcement, automation and online control is very important, as well as the simulation of the spraying process. And also we have a look on the surface qualities by post-processing projects. For further information, please have a look to our website. And I really like to thank you for your attention.
Hello everyone. My name is Erik Slange. I'm from Delft University of Technology in the Netherlands. I'm going to present this paper with the title Improving Printability of Limestone Calcined Clay-based Cementitious Materials. But let me first introduce my co-authors, which are Ozan Shoporolu and Yu Chen, also from Delft University. Yu Chen is actually the one that did most of this work, and he is also going to present the content after my short introduction. The content of this presentation is first a short introduction, then we'll discuss the material, then the printing setup that we use for 3D printing concrete. We will discuss the methodology that we followed in this research, discuss the test and results, finally conclusions and acknowledgements. 3D concrete printing can actually be defined as a fabrication method that employs an additive layer-based manufacturing technique to make 3D concrete components without formwork. There are actually two methods for 3D concrete printing. The first one is extrusion-based concrete printing, and the second one is particle or powder bed concrete printing. But there is more in concrete that can be printed. People in Karlsruhe Institute of Technology are working on 3D lattices, printed micro lattices that are actually stronger than steel but lighter than water. And we also want to do this in concrete. Here you see some of these 3D printed lattices out of polymer, PLA, but we also try to test them and model them, and we are going to make them out of cement paste and mortar and concrete. One of our PhD students, Yading Xu, is working on auxetic materials. Auxetic materials are materials with a negative Poisson ratio. They have a very huge deformation capacity and they can store energy. Another project that we are working on is 3D printing of the reinforcement in concrete structures. By printing the reinforcement, you can optimize the reinforcement and the location of the reinforcement, and in that way optimize the structural components. The final project that we are working on that I want to introduce to you is that we are dealing with modeling of 3D printing process. By modeling the process, we can optimize the material and the process for printing it. This was the last project I wanted to show you, and now Yu Chen will take over and he will tell you all the details about the topic that we discussed in this article.
We employed the extrusion-based method in our study. There are three strategies for extruding fresh mixtures: extrusion of very stiff or sufficiently stiff materials, as well as very flowable materials. Our study focused on developing the sufficiently stiff materials for 3D printing. A concern about sustainability is always highlighted when we talk about cement and concrete. So the first question, is 3D concrete printing belong to a kind of sustainable approach? The answer probably yes, because it doesn't need any formwork. It can reduce waste from formwork and potentially reduce the consumption of concrete materials. However, a problem needs to be raised here. The current printable materials may contain a lot of Portland cement due to the relatively low aggregate content. In this figure, there are several mixtures containing less content of Portland cement, which was replaced by high volume of fly ash. But the high volume of fly ash might result in low strength of the hardened concrete. Besides, common ISMs, for instance fly ash, slag, and silicon, cannot be used for long-term development of sustainable concrete due to the limited stock and uneven distribution. However, clays, especially kaolinic clay, which is the raw material of metakaolin, is widely available throughout the world, so calcium clay may be the best option of ICMs for developing sustainable cementitious materials. Massive studies have been done during the past 5 years. The advantages of using calcined clay as a kind of SM can be summarized as follows. So shall we develop a limestone calcined clay-based cementitious material for sustainable 3D concrete printing? But there are so many parameters need to be considered for developing 3D printing cementitious materials, such as the composition of bender, gradation of aggregate, fraction of different components, admixture, and fiber. This study only focuses on admixture section, especially viscosity modifying admixture. A HPMC-based viscosity modifying admixture was applied in our work. It could help to increase the viscosity and cohesion of the fresh mixture that showed sufficiently stiff for extrusion. But using a slightly higher dosage of VMA could increase the extrusion pressure significantly. Therefore, our objective is to investigate the effect of VMA on fresh and hardened properties of limestone calcined clay-based 3D printable cementitious materials, and eventually to find out the optimal dosage of VMA. For the material section, the chemical composition of bending materials, including Portland cement, a low-grade calcined clay that contains about 50% of metkaolin, and the limestone filler were characterized by XRF, XRD, particle size distribution. It is worth noting that the calcined clay used in this study shows a coarser particle size compared to others. The mixed design of studied mixtures is illustrated in the table. We kept everything identical except the dosage of VMA from 0 to 0.48% of the bender mass. The REF mixture is prepared following the track 1. For the mixture containing VMA, they are prepared according to track 2. The lab-scale 3D concrete printing setup in MicroLab comprises 3 components: a CNC machine, a material conveying pump on the basis of rotor-stator mechanism, and a hybrid by-hand downflow nozzle with a rectangle opening. The width of the nozzle is 40 mm and the height is about 13.5 mm. The detail of the conveying pump is displayed in this figure. We proposed a lab-scale protocol to investigate the effect of VMA on 3 specific aspects: fresh state behavior, 3D printability, and hardened property. For fresh state behaviors, how the flowability changes with time is studied. We mirror the height of the molded sample for the mixture containing VMA. After 25 times of table drops, the diameter of the sample is mirrored. But for the mixture REF, only the diameter of sample was mirrored before and after table drops. The flowability change can be clearly observed, especially after 90 minutes of water addition. For the mixture containing VMA, the workability loss with time passing is also evident. Increasing VMA dosage could enhance the shape stability and the retention of the demolded sample. The next test is based on a RAM extruder setup. 2 specific tests were performed to study how the extrusion pressure changes with time and how it changes with different RAM speeds. For the time-dependent property, a predefined protocol is applied at the different material edges to obtain the corresponding RAM extrusion pressure. Increasing VMA dosage could increase the extrusion pressure, especially for mixture for VMA. It shows an extremely high extrusion pressure even at a very early age. For different extrusion speeds, the material was only tested at the age of 10 minutes. The Basfield model also applied to fit the mirrored results and obtain some material flow parameters such as elongational yield stress, shear yield stress, and the flow consistency for comparing the difference between them. The mixture containing a high dosage of VMA showed a high extrusion pressure under the same speed. A good correlation between experimental results and the Basfield model was indicated. All flow parameters are increased by increasing VMA dosage. The last test in this aspect is grain strength test. Small cylinder samples were tested at the age from 30 minutes to 4 hours. The true stress and strain curves of different mixtures at different material ages are illustrated in this figure. Mixture 2 VMA shows a very close grain strength compared to 4 VMA, and both of them are much higher than 1.2 VMA. The second aspect is about the evaluation of 3D printability. Extrudability test aims to find out the proper material flow rate and nozzle moving speed. We applied different material flow rates and checked the corresponding pump pressure. Mixture 4 VMA shows very high pump pressure and easily to reach the maximum value of the allowed pressure. This also limits the printing speed of mixture 4 VMA. The second assessment is the open time. We printed one single filament with the length of 600 mm. The test started at the material age of 30 minutes with a 10-minute time interval, and the test was terminated once disruption occurred. A pre-sharing process is also occupied before printing in the time gap. The width of each printed filament is also mirrored to check the printing consistency. The results reveal that increasing VMA dosage lead to the reduction of open time, but it can benefit to the shape retention property. The last test about printability is buildability. A 5-layer object was printed by different mixtures. The height of printed object is mirrored to assess the shape stability. This test confirmed increasing VMA could enhance the shape stability of fresh mixtures. 2 VMA exhibited close results with 4 VMA. The last aspect is about Harden Properties. The effect of VMA on hydration was studied via isothermal calorimetry test. It could clearly show that increasing VMA dosage could retard the cement hydration. The 7-day compressive strength is tested on the printed samples at 3 different loading directions. Generally, increasing VMA dosage leads to the decrease of compressive strength, but mixture 2 VMA shows slightly higher strength than 1.2 VMA. The strength of hardened cementitious materials mainly influenced by the content of air void and capillary pores. To get more understanding about the microstructure of printed samples, we also performed the air void analysis. In air void analysis, the micrographs of printed sample are acquired from X-ray CT scanning, the obtained grayscale images were segmented using the trainable VK segmentation plugin from ImageJ. After processing all images, the results about 2D porosity are illustrated in this figure. Sample 2AMA showed the lowest 2D porosity, and the highest result is from sample 4AMA. But for sample 1.2 AMA, there are many coarse errors observed in the interface, which may be due to the extrusion-induced bleeding, the formation of lubrication layer, or a thin water layer. However, it is still not clear about that. The further study is highly required. Finally, we could conclude 0.24% of VMA is the optimal dosage in our study. Increasing the VMA dosage could lead to the following consequences. I'd like to acknowledge all the people who contribute to this work. And thanks for your attention. Do you have any questions?
Thank the organizers for inviting me to give this talk on 3D printable ECC, the strain hardening cementitious composite material. My name is Victor Lee from the University of Michigan. I want to thank my collaborators from Europe, from Asia, and from South Africa. And I want to particularly point to Freek Bos, who was instrumental in this collaborative effort. As we all know, as a brittle material, concrete construction requires steel reinforcements. Unfortunately, steel reinforcing and 3D printing are two processes that are not necessarily compatible with one another. The need for steel reinforcement becomes an impediment to the flexibility bestowed by 3D printing. For example, the ability to print complex geometry. And of course, the use of steel reinforcement also puts a limit on the efficiency of 3D printing as a new construction method. Now, this is the background for our introducing a self-reinforcing bendable concrete, ECC or SHCC. On my left, we see a slab of normal concrete fracture under bending load, reflecting the brittle nature of the material. On the right-hand side, we have a slab of ECC material similarly loaded, but instead of brittle fracture, it results in a deformed shape. The ductility of ECC is best exemplified by the tensile behavior. These curves are obtained by uniaxially tensioning a piece of ECC. And you can see that after the elastic range, it undergoes a pseudo-strain hardening behavior with as much as 4.5% strain. This large tensile strain capacity is roughly about 400 times that of normal concrete. ECC can also be made to have high strength. In this version, represented by the red curve, we see an ECC material that has compressive strength in excess of 200 megapascal. ECC is already a construction material in the real world. It has been used in this cable stay bridge in Hokkaido without expansion joints, and also used as coupling beams for seismic resistance in this tall building, the 60-story building in Cartagena. 3D printing of ECC is very similar to 3D printing of concrete, involving mixing, pumping, transporting through a hose to the nozzle where the material is extruded, the building of the structure, the curing and hardening processes. However, unlike normal concrete, all these processes can become much more complex with ECC, mainly due to the fact that it contains fibers. For example, during the mixing process, the mixing requirement is such that the material must have good fiber dispersion so that they don't clump together. During pumping, it must not clog the pump. It must be fluid enough to be transported through, pumped through the hose, a flexible hose, and then be extruded without causing a jam at the nozzle due to fibers again. And then, of course, during this extrusion process, there is a reorientation of the fiber, causing alignment or lack of in the built structure. ECC also needs to cure, given that 3D printed structures do not have formwork. So the direct exposure to the surrounding environment and how it cures is a topic of interest. And of course, we are very interested in the hardened property of structures and whether the printed 3D structure would be able to have structural integrity without heavily depending on steel reinforcements. During the extrusion process, the quality of the printed filament is directly related to the fresh properties of the ECC, including, for example, the yield strength, the plastic viscosity of the material, as well as depending on the ratio of the volume flow of the ECC material to the nozzle speed. And finally, the nozzle geometry also plays a role in controlling the quality of the printed filament. These dependencies have not yet been carefully studied and requires extensive experimentation in the future. One of the questions that we want to ask ourselves is, as a result of extrusion at the nozzle, whether the fibers will be aligned, as indicated in the left figure here, or whether it might be less than perfectly aligned with some amount of randomness, as indicated on the right-hand side. It turns out that both concepts have been supported depending on the details of the 3D printing process. For example, on the left, tensile stress strain curves clearly shows that the 3D printed specimens have higher strength as well as higher ductility compared to the cast specimens made of the same material but processed by casting rather than by 3D printing. Now this 3D printing is actually a simulated 3D printing with a caulking gun. On my right, you can see that the 3D printed specimen compared to the cast specimen of the same material shows roughly about the same strength and same ductility, about 3% strain capacity. This is 3D printed, by a robotic arm with a customized nozzle. So we see that the details of the stress strain behavior of the 3D printed ECC, while they all show good tensile strain capacity, the exact behavior depends on the print parameters, the nozzle details, including its geometry. Similarly, apart from the fibers, one can expect that 3D printing would also exert the influence on the matrix properties. This is a study by Putten et al., who shows that the printed mortars in these two layers, the center portion where the material is close to the interface between two adjacent layers tends to be more porous, as indicated in this micro CT scan image. And the larger pores are shifted to the right-hand side, as shown in this pore size distribution curves, compared to the lower and left portions of the printed filaments. Because of the higher porosity in the material near the interface between two layers, one can also expect that the interface would be weaker. And not only that, but also because of the potential lack of fiber bridging across the interfaces. In consideration of this effect, we conducted a study of the interfacial fracture behavior by casting a wall of layered ECC and then cutting it and turning this 90 degrees, and then introduce a notch and subject the whole assembly to a 3-point bending test. Not unexpectedly, we see a brittle behavior after the peak load is reached when the crack extends along the interface. But perhaps somewhat surprising is the fact that we see in all three specimens a kick up of the load deflection curve after the initial drop, and most likely a result of some amount of fibers crossing those two adjacent printed layers. This is likely a result of the interpenetration of the two layers of green ECC. The weakness of the interface can be overcome by the introduction of a groove. And in this case, we print the groove on the top of each layer. And as the next layer comes along and printed on top of the groove, the material penetrates into the groove and therefore form a tongue. And a tongue and groove joint provides interlocking so that when we test the specimen, now the test curve is very different and is very clearly indicating the effectiveness of the interlocking mechanism of the groove tongue joint, causing the propagation to be much more difficult compared to that of a smooth interface. These are just some highlights of research on ECC as a 3D printable ink. In the last year, we were able to print a twisted column about 1.5 meters tall with 150 layers, each of 1 centimeter thick, and the print speed is 1.5 meter per minute. We use a 6 degree of freedom robotic arm system combined with a progressive cavity pump at the nozzle, which takes the material from the hose, which is pumped through using a peristaltic pump connected to the mixer where the material is fed in. So to conclude, there has been progress made around the world on 3D printing of ECC or SHCC materials in the last several years. But as I indicated, there is plenty that needs to be further studied. Even as we demonstrate the potential of taking advantage of the self-reinforcing behavior of ECC for the purpose of diminishing the dependence on steel reinforcements. There remains a lack of deeper understanding of the interactions between materials and the sheets. This is particularly important where the material goes through the nozzle and got extruded. What has been demonstrated is that with 3D printing, it is possible to maintain the strain hardening capacity characteristics of ECC. And if one pays attention and do a bit more detailed investigations and research on the dependencies between fresh and hardened properties and the print parameters, I believe there is room for further improvements, perhaps to make the 3D printing as an advantageous process compared to regular casting process. So far, as I mentioned, we have accomplished building a 1.5 meter tall twisted column. This is obviously not enough, so there is a lot more work that needs to be done, and work where we need to maintain a good balance between pumpability and buildability. Further, there is a need to address the brittleness of the interface between two printed layers. We have demonstrated some initial success of using a groove thumb joint, but I believe that there is much more that can be done. Let me go a little bit more into needed research in the future. There is definitely a need for deeper understanding of the influence of the 3D printing process on the composite microstructure in the fiber matrix interface, and how that differs from regular casting process. The orientation of the fiber clearly is important in controlling the mechanical properties, as well as the anisotropic behavior of the printed layers, and therefore the structures. We need to deepen our understanding of the composite properties, both in the fresh state as well as in the hardened state. In the fresh state, the balancing of pumpability and buildability is always important for all concrete printing, 3D printing of concrete material, but definitely even more so in the 3D printing of ECC material. We need to look at the age dependency of the green properties of printed ECC. This is almost a completely open area where very little has been done. But this is critically important in maintaining integrity of the build-up structure as the printing is going on. And equally important are the subjects of drying shrinkage and curing. On the hardened properties, we need to look at the relationships between the composition, the ingredients, the composite properties, and the print parameters. I mentioned earlier the print parameters is going to influence the microstructure and therefore the composite properties. So these interrelationships are extremely important to investigate. And the anisotropic properties, both for tension and for compression, have not received enough attention. This is an area which is also important, particularly from the perspective of structural behavior and the ability to predict and simulate structural response under load. The interface behavior, I already mentioned, is very important. That could become a potential weakness, and therefore we must pay attention to both properly understanding the microstructure of the material near and at the interface, as well as how to characterize and control that behavior. And finally, for real-world applications, it's critically important that we have a better understanding of the durability of ECC printed structures and their structural integrity. The last topic that requires attention in the coming years would be greener versions of ECC material. That is, in fact, one of the drivers for 3D printing of ECC to reduce resource use, to speed up and increase construction efficiencies. And the need for greener versions of ECC has never been more urgent.
Welcome back to the main stage of Digital Concrete 2020. All our parallel presentations have come to an end, and I hope you enjoyed them and the discussions in the breakout sessions that followed. We are now reaching the end of our program, but we still have some excellent content lined up for you, with 2 more keynotes and the final episode of Science Meets Industry. My name is Rob Rolfs, and I will be the host for the first keynote of today by Professor Theo Salet. Theo Salet is Dean of the Department of the Built Environment and full Professor of Structural Design of Concrete Structures. His research spans from parametric design tools to nonlinear numerical analysis of concrete, with a focus on 3D concrete printing. Theo, welcome, and it's very nice to be here on stage together.
Thank you, Rob.
Our research group is known for its work on 3D concrete printing over the past years, from small-scale experiments to large-scale applications like the bicycle bridge in Gemert. Looking back to the past few years, but also ahead, is there a future for 3D printing in construction, and what does this future look like?
Yeah, Rob, our nature would be to answer this question from a perspective of the technology itself, but I think we have to look more on the societal aspects of this matter. Our industry faces issues with sustainability, and with that comes also the degree of freedom in designs, and issues with respect to productivity, be able to make enough affordable houses for future generations. And with that comes the issue of digitization. That's the title of this presentation, Working Towards an Industry 4.0. And we're not the only ones doing that. If you look back in history, what happened, different industries already invented that idea to look how digitization could be helpful to improve on issues regarding these societal issues, as you can see here on this slide. We as a group and more or less as a faculty as a whole work on that issue of digitization as well from different perspectives. So we work on digital twins. We also work on artificial intelligence tools combined with material tests and with algorithms to bring robots to life. So try to combine AI things with the issue of robotics. As a chair in our group, as you are familiar with, we focus on the issue of 3D printing of concrete, and this large-scale gantry printing robot, I think, is known to many of you already. And with that instrument, we made a first bridge in Gemert. And that was for the simple reason, coming back to your question for the meaning of the construction industry, to just try and have an effort in making something, show that to the industry and say, this is what we can do, please reflect on it and tell us if that is beneficial for your industry as such. What we realized from this kind of work that we did, it was the first time we did it, that it is relatively difficult. It's not self-evident. It comes with a price because it's a complex system. You cannot just print whatever you have designed. Material, the design, and the printer needs to come together. It's more or less a complex system that has to fit together and make a full set, a system as such.
Okay, so I guess it's important to emphasize that 3D concrete printing and other digital fabrication tools can provide an answer to these challenges in society, but at the same time it comes with an added complexity, and we have to address this as well. You wanted to illustrate this vision with 2 projects. Why these 2?
Yeah, I selected these 2 projects, a housing project Milestone that is currently being printed here in the city of Eindhoven as we speak, and a bridge project designed by Michiel van der Klei. And I selected these 2 projects to illustrate that our faculty of the built environment is a typical faculty where built environment, buildings, and civil engineering is combined into one faculty. So I selected these 2, and the second reason is that one is more difficult than the other, but I'll come back on that issue later on during this talk.
Well, then I hope you can tell us a bit more about these projects.
I would love to. Let's start with the building project. These buildings, and I guess you have seen the images before, mainly the important part is the plan view. If you have a look at the plan view, what we did is we approached the design from a perspective of that complex system that I just mentioned to you. And what we see here on the slide is that what we actually did is we printed corner elements, so volumetric elements, not a straight wall, but walls in a corner, curved walls, because they are stable in themselves. And they were printed on a slab. So actually what you have is a part of the slab of your building and a wall already on top of it, and that's a wall with a corner already in it. So it makes it very stable, it makes it easy for transportation. That's the plan, and in between these elements you could place framework elements and put your roof on top of it, so that the load bearing capacity is both on the framework and on your printed concrete. That's the plan, that was the idea. And all of these elements can be reused again, of course, because you can place them in a circular kind of economy in different plans of different buildings again. If we have a more closer look to these walls, what we see now is on the left-hand side an example that you print an inner and an outer wall, and you connect them, for instance, with the snake kind of thing that we see very often in 3D printing and extrusion processes. But if you make a real house, at the end, it must be comfortable as well. So you need to fill that in with insulation materials. Now, what you can see on the right-hand side is a first try for the fill-in, but imagine that that fill-in material could also be used for structural purposes, taking care of the shear capacity of the wall. Then you can cut down on the amount of concrete that you actually print. If that's the system that we are aiming for, it comes with a couple of questions. And for instance, in the fresh state, if you start to print this wall, it must be stable, and you want to optimize these sandwich kind of structures towards thinner and thinner walls over and over again, for reasons of sustainability. But then it must and remain stable during the printing phase, and your research work is a nice example of what we need to do in that case. The other issue is in the hardened stage, when the concrete is hardened, if you make it thinner and thinner, it comes with stability issues again. And again there, the presence of the insulation material should be beneficial and help the concrete not to buckle. So it's really a marriage between 2 materials here. At the end, if we make these walls, if you want to make it a system, you want to make them a system for real live buildings where people live in, you need to test them. And luckily, we are in a fortunate position here that we can do all these large-scale tests to see if the theory that we come up with also works into practice.
Okay, that's very clear. But up to now, you've mainly discussed the design and the concept of Project Milestone. But you mentioned also that it's important to consider the material and the 3D printer. Can you elaborate on these 2 topics as well?
Yeah, I guess the message was already sent by the first keynote speaker, Robert Flatt, who had a nice formula that's saying that If you look at sustainability, you have to consider the amount of material and the amount of cement per unit of material and multiply that together and divide that by the lifespan of your structure. So talking about reduction of concrete, I guess that's why we print, that's the additive manufacturing part. But yes, indeed, you need to discuss the amount of cement per unit of concrete as well. In our group, we work on that issue, and it's our colleague, Sandra Lucas, who unfortunately cannot attend this conference here because she just gave birth to her first son. But Sandra is working on the issue of the materials together with the design, because again, in a complex system, these two things come together. And her work focuses particularly on two things. The first is just sustainability from a perspective of emission-free concrete, making emission-free concrete. And on the second hand, of doing something different, and that is adding functionality to the concrete, so that the concrete no longer is only the load-bearing part of the structure, but maybe also is doing part of the insulation itself, or being there for electricity conductivity at some parts of the structure. So taking more than one function, which is also a way to increase on sustainability. And this is, for instance, an example, a more technical picture. On the left-hand side, you see a wall, just a traditional wall. Let's imagine it's 3 meters high, it is loaded, it's reinforced. But what structural engineers know is that the flow of forces in a wall do not need the full wall. Part of the walls are stressed in compression, part of the walls are stressed in tension, and in between there's hardly any need to have any material. So it would be a good idea to improvise or to improve on this one and come up with improvised solutions that give much more less concrete use. One typical way of working with that is, for instance, this. What Shishan Ahmed did, one of the PhD students that is about to graduate soon, he developed a grading type of material where material is deposited where you actually need it. So concrete that is strong, and at the same time at another place it is just taking care of, for instance, the thermal insulation. And imagine if you go back to the picture of the sandwich wall, if we could just print a sandwich wall, but at different places in the wall could apply different types of properties of a material, you have a kind of a hidden structure that you can't see with the naked eye, but one part is doing the structural part, another part, for instance, is doing the thermal insulation. Making things like that comes again with a price, with a cost. So you really need to do research, because at the end you want to be sure that the right concrete is at the right place with the right properties. And starting from that perspective, that at the end the properties of concrete must be good, you need to think backwards. What is it I need to do in my mixing, in my pump, with my hose to really get that done? And that's what Derek Bos, one of the PhD students now, is doing in his research here at our university. At the same time, you have to do something on your machine, on your robot as well. And this is one of the early things that we immediately did when we had our gantry robot. We mounted the machine so that we have always a fixed height of our next layer on top of the other layer, to be in control of that and avoid issues, for instance, with the poor bond that we heard a lot about already during this conference. Other issues what we do, for instance, to be in control is play with temperature, what temperature means on fresh concrete, and related to the stability issues, of course. And one of the most weird things that we ever did, and most of the time will do again in the future, I guess, is to be in control of fiber orientation even after printing by mechanical fields. Talking about that complexity, and maybe wrapping this part of my story up, is what we do is we do modeling, we do at the same time testing in the laboratory. But in this age, a third thing comes into the picture, and that's data. We're going to use data to add to that story and help us to solve the more complex issues. And that's your cup of tea in your research work.
Right, absolutely. And it was also Maarten Steinbuch, one of our keynote speakers on Tuesday, that said data is crucial. So we will have to start to combine numerical approaches to simulations with data-driven approaches like non-destructive measurements to be in full control of the process. And I think we can learn a lot by venturing into other fields and connecting with other industries to bring our technology one step ahead. Theo, before we move on to the next part of your presentation, I see some questions have come in the chat, and I would like to address a few of them to you. The first one is by Kees Lehmeyer, and his question is, will we shift from the design of a product towards the design of the process?
It's a definitely yes. So that's the case, because what we are normally doing, and there's nothing wrong with that in our industry, is to work towards a unique product. And we have to do the designing, we have to do the construction part. We have a difficult, a very long supply chain to get that done. And we need to do it over and over again because we're working on unique objects. That's the nature, I would say, of our industry. And I fully agree that we need to move on to a next phase where the process becomes much more important, working towards standardization of things. And that doesn't mean making them more boring. Yeah? I fully agree.
Okay. A second question comes in from Tim Wengler from the ATH. Theo, are concrete color printer plans still on the horizon? Printing multiple materials?
Yeah, that's an interesting one. Yes, I think we have to, more or less. And if color means not red, green, and blue, but different types of materials, why should we do everything in concrete? That's the question that would raise back to Timo, because there's no need to do everything in concrete. So let's make use of the material to its the way it is best. Concrete is good in compression, it's fire resistant, but let's try to use different and multiple types of materials and use the best out of each material from a sustainable perspective to come with valuable solutions for our society.
Okay, thank you. So let's go back to the system for a moment. You mentioned the sandwich structures as a concept, as a system in Project Milestone. But is this sandwich principle then the system for 3D concrete printing that we will move on with from now on?
Yeah, I raised that question myself a couple of times, and we heard from the lecture of Maarten Steinbuch earlier during his conference that he said that accuracy and speed are key. Mm-hmm. And he mentioned layer by layer, centimeter by centimeter. He challenged us to make speed. So what we've tried, and is something that you also said during his talk, just try something and come up with some alternatives and surprise maybe industry with that in order to find out if it meets their challenges. And this is an example. What you see here, for instance, is again a wall, but now not a sandwich wall, but on the left-hand side you see just a straight wall. What we did here is we intend to print that wall not vertically, but we intend to print it flat, so in the plan view, and then simply rotate it 19 degrees. If you do so, there's no need with the printer to print all these lines rectangular, as you can see on the left-hand side picture. You can make any kind of shapes, like the middle one. And the advantage of that is that you can start to optimize your flow of forces. And that means that you can cut down on the amount of material that you need. And normally people would do that maybe in a type of lattice kind of structure, but then you have to cross each node with your printer multiple times. And in order to reduce that, we come up with a more Voronoi picture like this, a pattern like this. But again here, you need something in addition on top of a lattice structure. You need an insulation material to take care of the shear forces in a structure like that. So similar to the sandwich element, where the insulation material, and that's maybe referring back to the question of Timothy, you need a second material here to take care of the shear forces. But at the same time, that material can take care of our thermal insulation. We call it stringer panel methods. It's a simple design tool, and it's very simple to design with tools like this. From that, we came to the idea, okay, let's move on and not optimize only from a structural perspective, but also optimize these walls from a perspective of, for instance, lighting, and make walls, facades, that are not structurally optimized only, but also optimized with respect to the amount of light coming inside our buildings. And with that came this picture. But you're questioning me, Rob, but actually this is the work of your studio this year. So I challenge you to explain the picture yourself.
Okay, I will. This is actually the excellent teamwork of 3 of our master students, Tessa, Irma, and Jelle. And what you see here from the top left to the bottom right is an optimization for 3D printing towards multiple criteria. So we start with an initial domain, and after a numerical analysis, we eventually end up with an optimized geometry. And this geometry takes into account both stress constraints, but also, like you mentioned, the daylight entrance. So we get bigger regions of openings, and we try to push them towards the top of the wall, so we maximize the daylight in the room. And the next step is to transfer this into a solid geometry and to generate print paths. And for that, we use evolutionary algorithms to select the best, the quickest print path within millions of solutions, making sure that also in the nodes, print lines do not cross, and that we have a proper anchorage of, for instance, reinforcement in these elements. So I think this is a very promising development in our field.
And again, Rob, I think you have to combine that again with the type of material that you use and the capabilities of your robot to make it a complex system again.
Absolutely.
Yeah. Yeah. Having said that, I think there is a downside to this thought, because before we are becoming too enthusiastic about it, there's also always a but. In this case, it's about the joints. The advantage of working on the milestone projects with these corner elements is that there are no joints, only the joint between the window frame and the concrete elements, but that's a non-structural joint. But if we work on wall structures and on slab structures, and we need to connect slabs and walls to walls together, there must be connections that are capable to carry loads. Now, this is a kind of an example of a dome that we made a long time ago already. It's called the Turtle for a reason, I guess. And the connections are relatively simple because a dome by nature is stressed in compression, so you expect only to have normal forces in the connections like this. However, if we move to the other structures that we just showed, the wall elements, we need to have connections that can carry loads in compression, tension, but also in shear, and hope maybe in the future in bending, but let's make that the next step, I would say. And that makes it more complicated. So we really need to look after that. One remark to this turtle is that take care if you design dome-shaped things like this, because with 3D concrete printing you want to make things much more light, and then the natural shape of a dome is not a dome anymore because the self-weight is not governing, but the wind load becomes the governing load, and the shape of the dome immediately starts to differ.
Okay, but Theo, you don't have to be a professor to know that concrete is good in compression, but not so good in tension. So when you start to introduce connections like this, and also when we start to optimize, we will have to address the issue of reinforcement.
Yes, Jimmy, I will address the issue of reinforcement. And we already addressed it a long time ago. Shishan Ahmed, I introduced him earlier during this talk, developed this tool to embed the reinforcement wires immediately during the print process. But that's one, making the tool is step one, but then the next step, of course, is to go further in this field and investigate the true meaning of the reinforcement systems like that for 3D printed concrete from a structural perspective. And that's the research field of Freek Bos, looking after the structural properties of reinforcement. And of course, you have to combine that again with the material, because one comes with the other. So the complexity is here again. And his research work is on finding out what the true meaning of reinforcement systems like this is in terms of bond between concrete and steel. It started with something like just confinement and is now developing towards things like real bending structures where the reinforcement needs to have a good bond with the concrete, as you can see on the picture here. But that's still reinforcing in the direction that we are more or less familiar with already. The next step that he takes, and he takes that step together with a PhD student, Laurie Haas, that you met before in this conference, working on the perpendicular direction. So that's reinforcing layer by layer perpendicular to the layers. And this, in this example, by using a screw type of reinforcement. Another idea of working on reinforcement, but okay, we can argue whether this is reinforcement or an improvement of the material, of course, is the introduction to introduce fibers into your matrix. The picture on the right-hand side, an old picture from the work of Zishan that he did embedding the fibers in the structure, is now being followed up by Karsten Nefs, another PhD student that you have seen here on the stage during the conference already. And he's working now on totally different types of fiber reinforced concrete, the more the ECC materials, where not only the fiber orientation matters, but where also the fiber shapes matters because they're not straight anymore. And what we always want to do, and I told you that in the beginning, try to do experimental research, do laboratory research, at the same time make numerical models and have that data AI tool available. And he is, for instance, here using an AI tool to get grip on the image capturing and making models from that, using neural networks to create these structures, as you can see here. And this is one of the examples of the numerical models that we use. This is just an example of one fiber being pulled out of concrete using cohesive zone modeling. And that's something that, to my pleasure, I saw during this conference as well from multiple authors working on issues like this. And then, maybe it's a bit tricky to say, but working on reinforcement in strut and tie and kind of structures using the tensile part as well in wall elements is maybe a small step towards using reinforcement in slabs. And this is a kind of an example of an optimized slabs, and we have seen multiple of these examples from different presenters during this conference and upfront as well, and I'm most happy with that. What we did here is we try to unreinforced, we make it reinforced as a slab, we made it pre-stressed as a slab, and we tried to make numerical design models that not only took into account where to place the material, but also how to deal with the pre-stressed ducts. So the level of pre-stressing was determined by the position of the load. So if you stand in the middle of the slab, the pre-stressing is differently from the moment that you step on the slab, just at the edge. And this technology is promising, but it's a little bit ahead of us, I would say. And one of the interesting things about this type of optimization is that we try to make use of the concrete to the best of its capability. So stressing compression, yes, we benefit that, but if the material is stressed in tension, we punish it a little bit. So that kind of algorithms are built in these design tools.
So from floor slabs and beams, it is not that big of a step towards bridges. And one of the first projects that you showed was also a bridge project. Do the same principles that you've showed us up to now also hold for such structures?
Yes, they do. But I have to make you a promise, so I have to keep my promise. Is it more difficult or more simple? And to my opinion, but it's just an experience of a couple of years, it's maybe more easy. If you look here together to the nice bridge designed by Michiel van der Klei, we try to realize this bridge. I made the mock-up and see if it actually holds. So actually here again we had a concept. The concept was this time print the cross sections. So you print the cross section of the bridge, and in this case it's not the bridge in GEMAT anymore with similar cross sections, but it's different types of cross sections that we have here. Each cross section was printed from a parametric model, obviously, and after that flipped over for 90 degrees and stacked together. In this mock-up, we glued all the elements together, but in the future, for reasons of circularity, of course, we would love to have cold joints so that everything can be reused again. So the principle is relatively simple. You print in a cross-section, you flip them over, and you stress them together. So it's a relatively simple concept, I would say. I showed you a big picture with a large-scale test, but everything starts from small. If you do a project like that, you have to start understanding your material properties first. So that's the research work that you did yourself, for instance, and many others here at the conference, joining the conference, finding out the properties of fresh material, by different tools, and finding out the properties of hardened materials and interface behavior as well. That's key. You need to know that before you can make any design and rely on your structure. And the final step, yeah, that's the step where you start to really test a long-scale bridge. And as I showed you, designing from the house that we made for Milestone, and going from Milestone to the different types of walls, you can go from that type of bridge to this type of a bridge. And again, the story of doing things big and doing things small matters here, because we on purposely ask you to be in this picture to make the bridge look a little bit bigger than it actually is.
Well, thank you, Theo. Perhaps you can share a serious note as well to end this keynote.
I will do. And I think I would be I like to do that. First of all, before I do that, I would like to tell that everything that I'm saying here is a result of a series of people that I just introduced, and that we are really in the fortunate position that we can even extend our group with the positions that you can see here on the screen. And it has a meaning that I show that to you. It's because I'm really proud on the team, but at the same time, it is because we as a team would like to stay with you, not only during this conference, but also the days and the months after. What we have experienced here, doing this conference in a online fashion, it was not only a hassle, but it also brought us something. It showed us that it's possible to be live together from a distance. And what we aim for and what we really offer to you, and hope that others will follow this idea, is to meet on a regular basis, exchange ideas on tests, maybe even put the cameras on the test facility, show the tests immediately so that you have a first impression on how things going from another part of the world, and have the data available as raw materials so that you can study them yourselves. Another idea is to exchange all the test setups. We have seen so many nice and wonderful test setups using this conference, but I would like to use them myself. And as a first step, I would say all the things that we use as test setups are available for all the other researchers worldwide as well. And that same counts for all the design tools that we develop. I'm a bit scary to share them, of course, because they're not perfect yet, but maybe that's the best to do, to share these products and ask our fellow peers to make them even better.
Okay, thank you very much, Theo. I think that's an excellent ending of this very interesting talk. We still have some time for questions, so let me take a look if some questions came up in the chat. The first one appearing is by Juliette Beckering, who is asking if the integration of services like electricity cables, water ducts, heating devices, and so on is in sight for 3D printed walls within this complex system.
At the moment, the answer is no. In terms of can we start working on that and use technology, use knowledge that is already available to really start working. No, that's not. But we are just a phase up front, I would say. We start to work, Sandra Lucas starts to work to develop these materials right now. That means that we need to do some research on developing materials that have these properties. Next step is we need to make them printable. And the step after is we need to apply them to something. But I would like to challenge Juliette and ask her to join us and to see if, from a design perspective, we can make designs that are made to make use of these materials. So that's where the complex systems comes in. This doesn't make totally no sense, us making new materials, if from a design perspective, there's no designs where they can be used in.
Exactly. I also see some questions coming in regarding the insulation material. If we are still using a conventional material right now, but what are the other answers in the way of insulation in the future?
Yeah, that's an issue. And maybe you saw that from the pictures that I showed, that we still use relatively environmental unfriendly insulation materials, simply for a reason that we don't know for others. Mm-hmm. So I'm really in a need for other researchers that can help us, other research fields that can help us to make materials, insulation materials that are much more nature friendly. on one hand. So I'm really in the need for help in that perspective, and you can imagine more of us are. The second thing is that we still connect them now to our concrete. And that's what I want to get rid of, because in a circular kind of an economy, if you use the insulation material together with the concrete, at the end of the lifespan of the structure, you want to separate both materials and treat them separately again. If you do not use the element as such, as a total, again, and reuse that again.
Yeah.
So it's two things. We need to work on the materials and have better insulation materials, and we need to work on the connections to be able to separate them.
Okay. So the nice thing is that in my room B, which I was hosting during this conference, I actually saw quite a few examples of lightweight concrete and foam concrete that were already printable. So I guess that's one of the first groups to team up with and see if we can combine these materials.
If we can make them a little bit ductile, that would be happy.
Right. Okay. One more question coming in regarding the structural simulation. So you mentioned the digital twins a few times. What are the key differences in structural simulations of 3D printed elements compared to conventional ones?
And is the question about the design of the structure or the research part, do you know?
I think it relates to the structural design.
Yeah. I think the big question here is how to design printed structures.
Exactly.
Is there a code for it? You have seen a couple of pictures that I showed, examples that we showed. The bridge in Gemert, for instance, and the other bridge in Nijmegen, the house project in Milestone. What we always try to do is have a permit. So that's our aim. And that makes it a huge challenge, because all of a sudden you need to design, and if I say we need to design, it's our industrial partners who need to design these buildings, and they're asking for how does this comply with the codes. The solution so far is not that difficult, because our codes, particularly the European codes, I must say, are not related to a kind of a manufacturing strategy. It's different in different parts of the world, so I should take care of my words here. But European codes are not. So we can make use of the codes that there are. And most of it will be on really knowing our material properties very well. And then from a structural perspective, look very carefully, what is it that my structure needs to do? And what is it that I expect that concrete that is made in layering by layering methods will be different about? And that's what you have to test. Most of the time we show these large-scale tests, and that's just to play safe, because we are the first one and we don't want to be the spoiler for all the rest. But eventually, at the end, it should not be doing all these large-scale tests, because then we make a bridge twice, once to demolish it in our test setups and once for the real bridge, and that's by far, of course, too expensive.
And not very sustainable.
Yeah, I agree with you.
A final question, it's a bit of an open question to you. What are some of the future developments that you would wish to see expand in the field? So let's say we are a few years from now, what would you like to really have achieved?
And then I come back to the way I opened this. I could answer your question from the perspective of the technology and say I would love to have a better robot, I would love to have a better mortar or a better design. But I think, and that's what I really hope, that it is really on the integration of this, on that complexity. What I hope is that we are able to make showcases of bridges and small houses like we're already doing. And that was the huge joy of this conference so far. That we are capable to make these examples, show that to our society, to our industry, and together with them, both just the people who have to live in these houses and the industry, work on examples and find out together where the benefit of this technology is. We love to work on this as researchers. And you can see in the conference people being here early in the morning at 5 o'clock and not wanting to leave at 12 o'clock in the evening. So that's such a strong signal. But if we can combine that, and that's my answer to your question, with looking for the real need to have an impact, that's what I wish for ourselves in the next future.
Okay. Thank you, Theo. I think these are perfect closing words for this keynote. Thank you for being here and for answering all of these questions.
It's my pleasure, Rob.
With that, we have come to the end of the first keynote of today. Now it's time for the final episode of Science Meets Industry. Enjoy.
Welcome at Eindhoven University of Technology. Normally this campus would be crowded with 15,000 students, but due to COVID-19, unfortunately, it's empty. And it's the reason that we cannot meet in person here at our campus, which is a pity, of course. At Eindhoven University of Technology, we develop new knowledge related to the issue matter of digital concrete. Sometimes in isolation, like fundamental research, but in this region of Eindhoven, mostly in close collaboration with our industrial partners. Eventually, all this knowledge needs to end at the industry in order to accommodate issues like sustainability, a larger degree of freedom in architectural design, and higher construction productivity. Today, we're going to visit the company Bruil, working on a unique renovation project with digital concrete.
Welcome at Bruil Prefab Printing. My name is Theo Voogd. I'm the Innovation Manager of Bruil. Bruil is a mid-sized company based in the Netherlands on 13 locations. We have 4 precast factories, 2 dry mortar factories, and also some ready-mix plants. We get in digital concrete printing because in 2013 and 14, the Netherlands were in a deep crisis. And we, as a traditional concrete company, had to innovate. So in 2015, we started to develop our own 3D printing technology, as well as the hardware, the software, and the dry mixture. So we're working on several projects, like a social housing project for 30 houses, where we will print the total wall construction. But the best known projects we are working on is the Watertaxistop in Rotterdam and project Baskeweg in Den Helder in the northern of the Netherlands. The structural principle of the Watertaxistop is based on 6 printed elements, double curved, which are joined together with pre-stressed cables. Applying pre-stressed cables in a curved construction is of course very complex, but with a lot of testing and the help of experts like DSZ, we made it happen. We use steel plates in between the elements to center the cables and align them into the construction. The cables are fixed between the foundation and a steel end plate on the top. To get a permit for this kind of project, we have to prove it by design by testing. So we built the entire Watertaxistop and pushed it to the limits so that we can find the weak spot in the design and can improve it for the final version, which we are building right now. What we learned is that this construction is not only possible in theory, but also in practice. Of course, a good relationship with the municipality of Rotterdam is really important for this kind of projects. They need to have confidence in what you are going to create. For instance, the material was very important for them. So we are making and printing with real concrete so that the regulation will fit to this kind of constructions. Our star project at the moment is project Baskeweg in Den Helder. Here we're going to upgrade 2 apartment buildings of in total more than 150 apartments. The project consists in total 1,200 3D printed elements like facade panels, balustrades and columns. The client wants to have bigger balconies on the existing building, so we place in front of the facade a new structure. The 3D printed elements are attached to the new structure. The new structure is carrying all the weight and is only attached to the existing building. In this building, we have more than 160 different shapes and sizes. During the design phase, the complete building is 3D scanned, and the point cloud is the base for the rest of the design. With 3D printing, it's very easy to make all the elements for this kind of projects, because every element could have another size or shape. Even the difference between the two apartment buildings are really small, but we can easily adapt these changes to the models. And this particular project is chosen for renovation because it's more affordable and it's more sustainable. 3D printing is often seen in new projects, but this particular case shows that it's also really suitable for existing buildings to renovate them or to upgrade them. We are very proud of this project because it would never have been achieved without 3D printing. Of course, we can't achieve this kind of project without the help of extraordinary partners like Cocon, Movares and Eindhoven, and of course our client, Helder Vastgoed.
My name is Elise Buiter and I'm an innovation engineer here at Brel. 3 years ago I came to Brel and then we had a good prototype 3D printer. It was my role to turn this prototype into a production machine and to create the entire process around the 3D printer. To be able to print multiple objects in a day, we have placed the robot on the track so that we have a greater reach and that the elements have time to settle and to harden before we need to remove them again. What makes this location unique is that we do not just have a 3D printer, but we've created an entire production line where you can also coat the elements, but also saw them so they can be attached to the existing building. One of the strengths of our 3D printer is that we have a high control over our print head. So we can orient it in different directions to create free-form elements, but also we have very high control over the amount of material which is deposited, so that we are able to make very accurate elements. An architect gives us a 3D model. This model probably comes from his parametric model. This model is then translated into robot code, almost fully automatically, and this robot code contains all the information necessary for production, how the robot should move and how much material needs to be deposited. As soon as the production line has been started and the right robot code has been selected, the process is fully automatic and does not require any human intervention. In this way, we have a fast, fully automatic production process, and this also creates a very safe working environment. After production, we also use a 3D scanner to check the printed models with the original 3D model. For the future, we want to make new concrete mixes where we use more recycled materials to increase the circularity of the product. For Brel, it is important that any new materials that are developed fall within the current regulations, so that we are able to create products such as the Baskeweg. With 3D printing, we do not need formwork, and the production process also has low waste. So therefore, this production process already has a low carbon footprint. Next to this, 3D printing gives you the ability to print hollow objects. For a project such as the watertaxi stop, we use 40% of the material that we would have used if we would have used traditional casting methods. We believe that the choice between prefab printing or on-site printing depends completely on the project and the location. Sometimes you want very reliable building elements, so you'll choose for prefab printing, and sometimes you need to transport the elements over a very long distance, and then on-site fabrication might be the logical choice. We believe that 3D printing will enable the growth of digital fabrication in the entire sector. We would like to challenge you to look beyond 3D printing. Sure, we can print a 3D element here, but how do we use this product in the built environment? How can we attach such a 3D printed element to an existing building?
So now, welcome back. We are really almost to the end of Digital Concrete 2020, but we have something special for you still. First, we will have our final keynote by Virginia Sanfratello, and then we will also have, also very important, the conference award. So don't go anywhere. or perhaps I should say, you can go anywhere, just stay online. Joining us now is our final keynote speaker, Virginia Sanfratello. Virginia draws, builds, 3D prints, teaches, and writes about architecture. That's really a lot of things to do about architecture. And she treats it as a cultural and therefore deeply influenced by craft traditions and contemporary technology. So really looking for that connection between craft and contemporary technology. She's a founding partner of Emerging Objects and has done some amazing work in the field of 3D printing in architecture, as we are about to witness. Virginia, it's very early on your side. Thank you so much for joining. How are you?
I'm well, thank you, Frank. Good afternoon to you.
Thank you. Thank you. So over the last 4 days, I feel that we have really heard just about anything that you can learn about printing with cementitious materials in any kind of shape or form that you can imagine. And it's actually coming to the point that I'm hoping a little bit that maybe you can take our blinders off a little bit and open up our eyes to the world of printable materials.
Oh, thank you. Yes, we have done some 3D printing with cementitious materials, but we've also experimented with numerous other materials, and I'm delighted to have the opportunity to walk you through some of those experiments today.
Please do.
All right. As you mentioned, I'm a founder in the company Emerging Objects. And at Emerging Objects, we're attempting to use materials in the waste stream, such as sawdust and rubber tires, and plentiful and inexpensive materials such as salt, cement, sand, and mud to create sophisticated building materials for 3D printed architecture. And we've been developing these materials for 3D printing for the last 10 years. Many existing proprietary materials currently available for 3D printing are prohibitively expensive for use in large-scale printing, which is one of the things that led us to search for new material palettes. So today I'm going to take you on a journey through some of the materials that we've developed as we think about printing architecture and printing big. But I want to start by talking about a material that most of us can find at home on our own kitchen table. Coffee, for example. Of course, coffee is used to flavor water for drinking, but I think it's also essential to understand how flavoring itself and how objects for the built environment can quite literally be flavored in terms of texture, color, and aroma by their inherent materiality. So materials such as coffee flour have the ability to be transformed through 3D printing. The production and consumption of coffee offers many opportunities to harvest waste. Starting in the field where coffee beans are picked is one of the first opportunities. The coffee bean, of course, can be found at the center of the coffee tree's fruit, or the coffee cherry as it's called. And the bean goes through the process of drying or washing as it's separated from the cherry pulp. And the bean continues on its path to become the coffee that we know, but the cherry is left to rot in the field, and it's an agricultural waste product. It often gets dumped into rivers or left in heaps. Coffee flour, however, is a new product that can be made by collecting, drying, and pulverizing those cherries into a powder that's certainly edible, but it also has excellent 3D printing capabilities, as evidenced here in these flavorful and aromatic 3D printed coffee cups. Coffee grounds are also useful for 3D printing. These grounds have been collected and recycled from my own kitchen, and they're used here to print this coffee pot. Materials such as sugar can also easily be 3D printed because of sugar's inherent solubility and stickiness. It's possible to print the sweetest of confections. And in this case, the sugar spoons are printed in volumes corresponding to 1 teaspoon, 2 teaspoons, 1 tablespoon, and beyond. And of course, your sugar spoons can be stirred down and dissolved into your coffee to flavor it with sweetness. One can also find tea waste being generated in the field during production and post-consumption, similar to coffee. And tea can be shaped into functional objects such as these teaspoons. The teaspoons are flavored with sugar and lemon, and they also dissolve in hot water to become fragrant with a syrupy aroma of herbs. And of course, there are teacups and a 3D printed teapot, no less. Chardonnay grape skins. We use pomace, which are the solid remains of grapes after pressing the fruit to make wine. The pomace includes the skin, the pulp, the seeds, the stems of the fruit. Traditionally, of course, in Italy, this is used to make grappa. In the United States, we don't use that to make grappa. We use it as fodder to feed animals. But there's another potential use for grape skins, which of course includes 3D printing. And we've printed these goblets out of Chardonnay grape skins from close by Sonoma. This is a 3D printed Chardonnay building block, which is radial arrayed to create this ice bucket for Pierre Jouet. And an attempt to create a new color inspired us to print with curry. This 3D printed furry curry casserole dish makes for literally a mouth-watering object. We were looking for color, but what we found was aroma and the scent of this object as it's printing. And even now, maybe 2 years later, is pervasive into any space where this object finds itself. And this curry dish is not only aromatic, but we imagine it to be a functional vessel that would also season the food, the rice or the noodles that would be placed in it for serving. And of course, it's always important to end with something sweet, cotton candy. This cotton candy jar is both made of and filled with sweet scented strawberry flavored candy. Perhaps the most frequently used material for flavoring, however, is salt. Salt can be 3D printed and formed into objects that we're familiar with, such as these functional 3D printed salt shakers. Salt always has beautiful optical properties of translucency, no matter how thinly or thickly it's printed. And it can be formed into flavorful building blocks of the future, which you can see here. The salt blocks can be shaped into forms that are otherwise impossible to make with traditional molds or casting. And we've experimented with different methods of interlocking and stacking these blocks. Because I'm located in the San Francisco Bay Area, this is a local material for me. Salt has been industrially harvested in the Bay Area for over 150 years. And at the peak of production, the Bay Area produced 40,000 acres of salt and 1.3 million tons of salt annually. And this is using only the sun and the wind to farm this crop. These days, about 150,000 tons are harvested in the fall from the bay. So this is an example of the salt that's accrued, I think, usually around the end of October, the beginning of November. And the company that owns the salt crystallizers in the bay has more recently given 16,500 acres of land to the government for wildlife redevelopment. And an additional 1,400 acres has been set aside for a residential development of 12,000 homes, which would accommodate around 30,000 people, which for us raised the question, does salt have the potential to be a building material for this development, should it happen? And so we imagined the possibility of bringing salt and glue together to kind of make a salty glue, if you will. And we looked at very traditional forms of salt extraction and boiling. We were really inspired by these domes and baskets that were originally used to harvest the salt crystals. And we designed individual tiles using crystalline forms inspired by the salt itself. And we printed 330 salt crystal tiles, which we arrayed around an igloo form to create this enclosure, which we call the salty glue. And we feel like, because of the optical properties of the salt, the interior is literally seasoned with diffuse light, if you will. And of course, there's an exterior that protects. And we imagine using salt to define interior spaces, such as bedrooms and bathrooms, spaces that require privacy, but would also benefit from the faint glow of dispersed light into the interior. Other agricultural materials that we've developed for additive manufacturing include sawdust. 7.1 million tons of wood waste are generated in the United States each year. And of this amount, 67% is potentially recoverable. And we wanted to discover if we could recover this waste material to create a 3D printed wood material. And we have. So we've been able to use this material additively instead of subtractively. And we've developed a formula that takes advantage of fibers to give increased tensile strength. And one of my favorite things about 3D printing with sawdust is that we're able to create a kind of artificial grain in the wood, depending on the orientation of the digital model within the print bed itself. And when printed thinly enough, the wood can be translucent. And we've experimented with different species of wood. This, for example, is pine. This is maple. And this is walnut. And we've aggregated these walnut tiles together to create what we call the sawdust screen, which is an interior partition that has openings in it which allow for the passage of light and air and views. We've also experimented with 3D printing rubber tires. In the United States alone, approximately 290 million scrap tires are disposed of every year. Around 80% of these tires are recycled, but we'd like to find new applications for the rest of those 60 million tires that aren't. Now, this is the largest tire landfill in the world. It's in the Middle East, and you can see it from outer space. So if you look down at the bottom of the image, you'll see these are buildings, and this just gives you a sense of scale. So we feel strongly that this material needs to find another in-use purpose. We've partnered with a company called Lehigh Technologies that makes a product that they call MRP, a micronized rubber powder, that's generated through a cryogenic manufacturing process. The tires are frozen, reduced to crumb, and then ground into a fine mesh, which is typically used in roofing or asphalt pavement. And we're able to 3D print with this material. And we have slowly been able to perfect this formula to make a more refined finish. And imagine the possibility of using it to create furniture such as this rubber poof, which one could find outside, maybe at playgrounds or bus stops, and other exterior materials or applications for this material, I should say. And of course, cement, which is the most ubiquitous building material in the world. But it has to change for 3D printing, as we all know. And of course, one of the advantages of printing with cement is that no formwork is required. Formwork can be, up to 60% of the cost of construction. We've created a fiber reinforced cement polymer for 3D printing using binder printing, which of course allows for file to fabrication process. Our 3D printed cement has structural capabilities when fiber reinforced. Our cement polymer, after printing, has a compressive strength of around 4,700 PSI. Typical concrete is 3,000 PSI for comparison. And when printed thinly enough, it's translucent. We've experimented with different finishes. So here, for example, we've sandblasted the 3D printed cement so you can see the layers from the additive manufacturing process. We've experimented with different techniques for aggregating parts to make larger assemblies. This is an early test where we just use binder clips to hold pieces together. These are the parts that make up Andrew Cudliss's P-ball. Here you can see every part is unique and different, but it they come together to make this beautiful, perfect object. And of course, one of my favorite things about 3D printing and additive manufacturing is that the digital model I use to make this small study model is the same one that I can use to 3D print this larger cement pavilion, which we call Bloom. Bloom is Tempietto. It's about, I think, 12 feet in diameter and 9 feet tall, and it has this custom image of flowers mapped onto its surface. It's a project that we did with Siam cement in Thailand using their iron oxide free cement, which is white. And here you can see the black and white image that we cylindrically mapped on the surface of the Bloom structure. The white from that black and white image in the graphic becomes the solid area, and the black is translated to openings within the surface that allow, again, for the transmission of light, air, and views through this visual motif. The tiles are printed either 1 or 2 at a time in a traditional Z-Corp 310 printer. So here you can see some of the deeper tiles at the bottom of this image. They're about 4 to 5 inches deep, and they have holes in them for mechanical fastening. And as we move up to the top of the pavilion, the tiles become much thinner, only around 1 inch deep, so we could print more tiles at a time, but also reduce the weight of the structure as we moved up. This slide just shows an example of how we print out the full-scale floor plan of the building itself and lay out the blocks for assembly. And this sequence of images shows the assembly process. So we print the full-scale image, lay out the blocks, and then subsequently every piece goes into place perfectly. And then we take it apart and leave it in chunks so it can be assembled quickly in the future. And in this video, you can see an example of the chunks of the smaller blocks that are being erected. So it literally only takes maybe 3 or 4 hours to put this pavilion together now. And here it is at the University of California on display. And again, you can see through that visual motif, the pattern being illuminated by interior lights. And the interior is quite different. It has a very different reading. On the exterior, you see the pattern of the flowers. And on the interior, you start to understand the structure of the pavilion. So each block itself has a cross inside of it. And this cross transfers the loads from the top to the bottom. And it's a completely self-supporting structure.
So thank you very much, Virginia. Must say I'm amazed. I'm beginning to wonder if there's any material that we cannot print with. And I think if I see what's happening in the chat, that people are also fascinated by this. There's a lot of people, and I think they want to know all the technical tricks behind it. And maybe a good question to summarize it is Professor Erik Slange is asking, can you put coffee in the coffee printed coffee cup?
Yes, you can.
So the slide of kind of the question behind it is, I guess, what kind of binder did you use that it doesn't dissolve when you put hot water in it?
So that's a good question. I mean, there are two ways to think about drinking coffee out of the coffee cup. And one is that, well, to answer his question, the binder that we use is mostly water with a little bit of alcohol, but then we post-process the pieces with a 2-part epoxy. And we've used an epoxy that is food safe. So you could pour coffee into your coffee cup. The other idea is that we could just epoxy the exterior, and then you could pour hot water in, and that coffee that's been 3D printed, that's in a relatively fragile state, would dissolve and become the coffee that you drink. So that's how we do it. And those are two ways to possibly consume your 3D printed coffee.
I was really relieved to hear that you make it actually from the waste material that comes with the coffee production. At the first instance, I thought, oh, I hope she's not taking away my coffee. But another question, so all these materials, do you print them on the same printer or a similar type of printer?
Yes, most of those were printed on Z Corp 310. We also use Projet, 3D Systems printers, the Projet, I think the 450s and the 860s. So we've used 3 or 4 different types of printers, but they're all powder-based binder printers that we've modified to suit our purposes.
So it's rather interchangeable, actually.
Yes.
Interesting. I think so there are more questions in the chat. Maybe you can join there later and answer some of the questions. I think people are really curious about it. But what I'd also like to know is that we have all this palette of printable materials, but what use are they in the construction industry or the built environment? Have you made any architecture projects with these?
Yes, we have. And we've had the opportunity, I should say, to build a small cabin in Oakland, California, which we call the Cabin of 3D Printed Curiosities. This is a building that we built in response to the housing crisis in the Bay Area, because there are insufficient places for people to live that are affordable. The cities of San Francisco and Berkeley and Oakland have all relaxed their zoning laws and allow for AUDs or ancillary units, dwelling units that can be occupied to be built in backyards without any design review. So you don't have to get a building permit. You don't have to have the building inspector come out to examine the architecture. And we thought this would be a great opportunity to employ some of the materials that we've been experimenting with. So on this cabin, on the front facade, we've clad it with planter tiles that are made out of some of the various materials that we've been experimenting with. So for example, if you look closely here, you can see these dark brown tiles that look like they're about 80% dark chocolate. And these are made out of the Chardonnay grape skins from Sonoma. The very light brown tiles that are a caramel color are made out of sawdust from the Sierra Nevadas. And the light gray tiles are cement. And every once in a while, we'll mix all 3 materials together. We use our own waste and we put it in the printer and we print that. So sometimes we get different colors as a product of that mixture. And these tiles hold succulents that thrive in the mild Northern California climate. And we built this about 2.5 years ago. So we've been watching how these materials age and weather in the climate. And you can see they're changing, they're transforming, but they're still quite beautiful as they age. And on the east and west facades and the roof, we've 3D printed around 5,000 ceramic tiles to make up a rain screen that will protect the building as well. And we used a local California clay body and paste extrusion to print these tiles, which we call the seed stitch tiles, which is a technique in knitting, which looks like seeds have been kind of strewn or thrown across the surface of the knitted object. And we really like the way these tiles bring a kind of soft texture to the facade. And if you look closely here, you can see they have a very simple method of attachment. There's just a hook at the top, which hangs on a J bead, and then the tile on top overlaps, which keeps it in place and prevents uplift on a windy or rainy day. And on the building, the tiles create this kind of zigzag pattern and cast shadows on themselves throughout the day as the sun shifts. And you can see vines from the garden are starting to weave their way through the tiles, and they build bridges between the landscape and the architecture itself. The walls and the ceiling on the interior are clad with a bioplastic panel, which we printed using FDM printing techniques. And the surface quality or the texture that you see here references traditional press tin ceilings and walls from the era of the surrounding Victorian houses in this neighborhood. Traditionally, of course, press tin sheets were stamped one at a time using cast iron molds, and the molds were often painted white to give the appearance of hand-carved plaster. But in this case, instead of having a mold and one repeated tile, we have complete variability. Every tile here is different. And we really love the kind of soft sheen that this material has. We've also printed the chairs and the side tables, which you can see here in this photograph as well. And of course, through 3D printing, we're able to achieve the same effect of a highly intricate and sculptural surface that might have been made to resemble molded plaster or pressed tin, but it's something entirely new. And the digital nature of printing allows this to be uniquely patterned and uniquely shaped. And the bioplastic is opaque during the day, but it's backlit with LED lights. And so at night, it transforms the space. We were surprised to find that the bioplastic, even the opaque material, is translucent when backlit. So these walls become luminous and they're color changing. They take on the color of the light behind them and create a surface that transforms chromatically and texturally to invite different activities.
So that's I'm just amazed by the the fact that you can actually take all these materials and apply them in such a beautiful building. We get a lot of compliments for you, Virginia, in the chat as well. Professor Juliette Beckering is asking if you can build with the salt elements. Are they structurally strong enough to make a real structure? Maybe something beyond the salty glue that you already showed.
Yes. So again, the binder is water with a little bit of alcohol, but because we post-process them with the epoxy, they do have structural capabilities, so they won't melt. So we could build something with them, yes.
That's wonderful. And this, the last project you showed, I'm particularly curious about the durability of all these materials. So how long has it been out in the open?
We finished it in early, I think, February of 2018. So it's been almost 3 years, 2.5 years. And it's been a great opportunity to see how the building weathers and how it performs. And of course, the ceramic is fine. It'll probably be fine for 30,000 years, right?
Yeah.
We were mostly curious about the Chardonnay and the sawdust and the cement, and they're changing colors, but they're still fine as well, which is exciting to see.
Yeah, wonderful. I'll be interested to follow how that develops over the years. And what about what you're doing now? Are you still in these kinds of projects or other materials, or what are you working on?
We are currently working on a project called Mud Frontiers. This started, I guess, about 2.5 years ago in 2018. We did this research with 3D printing clay, mud, and Adobe for an exhibition titled Future Ruins, which happened at the Rubin Center at the University of Texas, El Paso. we had an opportunity to go with students from the university to harvest wild clays in both the United States, Texas and New Mexico, and Mexico. So we dug clay in Chihuahua, in all these areas around the border between the United States and Mexico, and we were amazed to find all these different colors of clay, and we thought the variety and the complexion of the clay at the border was so beautiful. We've also been developing our own software as part of this project. It's called Potterware. It's a software that's very easy to use. It runs in the cloud, and you can see on the right-hand side of the screen that users can just slide these dots or bars to change the geometry of the G code, which is being generated for 3D printing vessels. And we did this to kind of lower the bar so that students or users who had never 3D modeled anything or 3D printed anything could very easily and very quickly design something that they could make. And we've continued to improve the software. So here you can see we're experimenting with non-planar printing, giving users the ability to make multiple prints, for example. And the students who dug the clays, we gave them access to this software. We gave them a 3D printer, and they printed 170 vessels using this clay that they dug, which was amazing because these students had never 3D printed anything before. They had never modeled anything in the computer before. And literally within like 2 or 3 days, they were up and running. So that for us was particularly exciting to have the ability to share this knowledge and these skills with a new group of users. And so here you can just see a close up of some of the beautiful vessels that they made. And parallel to that, to excavating the local clays, we were digging mud to make large scale Adobe prints as well. So the students worked with us on this too. And we have a new large format SCARA printer that we have designed to print building size walls and objects in the landscape. So here we are with our SCARA robotic arm or 3D printer, printing on a mesa in El Paso overlooking Juarez. And we call this project Mud Frontiers for 2 reasons. One, because we're literally printing at the border, the frontier between the United States and Mexico. And 2, because we're exploring technological frontiers through the lens of mud, which is a very traditional building material in this region and most of the southwestern part of the United States. So in this image, we've taken the robotic arm inside the gallery and brought in the local clays and printed this enclosure. It's about 7 feet wide and 8 feet tall. And you can see the robot arm is much smaller than the object that's being printed. And here we're able to demonstrate the capability of using this material that local communities have built their homes and places of worship and work out of for thousands of years. And we're able to do this again. And here you can see the 3D printed Adobe structure with the vessels that the students made in the background. And then last year, we took the robotic setup to the San Luis Valley in southern Colorado, which is where I am now. And this is our fabrication setup. So if you look at the bottom of the image, you can see our wheelbarrow full of local mud that we're digging on site here, using the tacit knowledge of the community. Again, this is a region, it's actually the traditional or the historic border between the United States and Mexico. Houses and buildings have been made for hundreds and thousands of years out of mud here. The Taos Pueblo is here. This is the longest continuously occupied building in North America. It's a multi-story mud structure. So we're using the local mud, we're depositing it into a hopper. The hopper is connected to a hose, which is held in place by the backhoe. And then the hose is connected to the robot, and you can see this lacy-like structure that's being 3D printed out of the mud. And last summer we printed 4 objects, and we kind of experimented with them under 4 different themes. We called them the lookout, the hearth, the beacon, and the kiln. And what you're looking at now is the beacon, which is under construction. This structure, pavilion, explores how texture and undulation of the 3D printed coil of mud can produce the thinnest possible cross-section for enclosure. So this is one single line of clay. The coils are then illuminated at night to show, I think, the contrast or the difference between the convex and concave surfaces that create the mud walls. We've 3D printed a staircase, and we use this layering up of the coils to create a structure that one can walk on. And we call this structure the lookout. So you see the dense network of coils and how they add together to make the structure that underlies a platform and each step itself. We also imagine that this dense, thick structure could have insulative properties. We're in a very cold region of the United States. In the winter, the temperature drops to minus 20 degrees Fahrenheit here. We use this structure as a kiln. It employs some of the techniques already discussed, interlocking to create an inner and an outer layer of structure. This is an enclosed area that draws in oxygen. It keeps heat in the fire. And we use this to fire locally sourced clay with juniper, which burns very hot. And these are just some of the smaller objects that we fired in that 3D printed kiln. This is a local micaceous clay that we've dug in the mountains surrounding this region. It has this beautiful shimmer to it because of the mica in it. And the 4th experiment is called the hearth. So this was an experiment where we printed an inner and an outer coil of mud, and we tied the 2 layers together with these juniper sticks, which have kind of structural value. It allowed us to print a little bit faster. We were able to print, I think, up to 18 to 20 inches a day instead of maybe 16 or 14 inches a day. And it gives this furry texture on the exterior of the building. And this is the interior. So for us, this project unearths and re-examines ancient building traditions and materials, but it simultaneously uses 21st century technology, craft, coupled with local skills and tacit knowledge to create emerging, new, and sustainable traditions. And now in the last 3 weeks, we've started printing again. We are attempting to make a larger structure. What you see here are the foundations of a house, an unnamed house that is currently being fabricated. It is about 8 meters long and will ultimately be around 4 meters high. And in this instance, you can see we've placed the robot on a rail that we've built, a plywood rail, so we can move the robot from room to room and print continuously throughout the day. And here's just an example of robot extruding the clay. Again, we're using the inner and outer coils. And you can see there are 3 rooms. I'll show you a little video that walks you through the rooms. Here are the ideas that we're making. A first room that will be a sleeping room, a second room, which will be a living room. It has a hearth and 3D printed mud benches. And then this third room has a sunken bath and will be a bathing area. So we're getting closer to creating occupiable, functional architecture and not just a pavilion. We have exceeded the height of the robot in the fabrication, actually just this past Friday. So we built a plywood box to put the robot on so that we could print taller. This is a photograph from 2 days ago. So we are about 2/3 of the way up. So the walls are now, I think, about 2 meters high. They will ultimately be 4 meters high. At this point, we have used about 30 tons of mud to print these 3 structures. And we've finally been able to take one of them to the full height of 4 meters. In 2018, on the 40th anniversary of the Smithsonian Magazine, they made 40 predictions for the future. And the first one was that sophisticated buildings of the future will be made out of mud. And it's our aim to make that prediction come true. Thank you.
Thank you very much, Virginia, for this wonderful presentation. Also, this last project of the series of projects really was quite spectacular, and it seems to make so much sense. I think, I mean, local earths and muds and clays have been used really around the globe, maybe almost forever, to make buildings. Certainly here also in the Netherlands, we've been using the local clays to make bricks, which hold up most of our historic buildings. I was wondering about that. The clays. Is there any kind of baking or post-processing needed to be able to use them in a longer term?
No, we're literally just digging the ground beneath our feet, and it's a really good combination of sand and clay here. We add chopped straw to it, barley straw and water, and we've kind of, I think, developed a mixture that's similar to what you would use to make Adobe. And it's sun-baked and it's strong. I think ultimately we'll probably put a roof over this to protect it from the rain and the snow, but otherwise it's quite strong.
Okay, yeah. Sun-baked is a kind of a technology that doesn't work in the Netherlands. We only have rain-baked, unfortunately. We have a question that came in from Vera Foni is, do you stabilize the earth that you're using?
With cement? No.
Yeah, I think that is the background of the question, yeah.
Yeah, no, it's just mud.
Okay, well, thanks. And the other thing I find very fascinating and is the way that you've been working with students and that you've kind of given them the tools to start designing and then making things themselves. So one of the things maybe was not touched upon in this conference so much, but I think will be a real question for the future also, is how do we bring all these new technologies to our students, and how can we kind of make sure that all the things that we are developing and thinking of somehow find their way into practice. And I think it's very good that you're kind of also developing tools that are easy to use in a certain on a user level, so that they can actually start to make things with this material and with this technology. I am really grateful for that you have been here with us and that you were here this morning. Well, for you. Then I say goodbye to you, and we move on to the closing part of our conference. So thank you very much.
Thank you. It's been a pleasure.
Okay. Bye-bye. So now we are really getting close to the end. There's just a couple more things that we need to cover. One of the important things that we still need to do, obviously, is the conference awards, because really, what is a conference without awards? But I keep you in suspense for a little longer, because I also have two things, practical things that I need to communicate before that. And I'm a little bit worried that if I do the awards first, then you won't have the patience for this. So the two things are, one, practical. The platform that you're on now will be open and accessible until Sunday morning, 9 o'clock, so early. So if there's any documents you want to download, presentations you want to review, you have a couple of days extra time to do it, but take that time because not everything will be available after that. So keep that in mind. Your ticket is valid until Sunday morning, 9 a.m. Central European Time. That's the one thing. The other thing is we have been very glad to be able to bring you this conference online in the way we did. We are also very glad with the number of people that have been willing to join. Not only willing to join, but also to join in such an active way. So we've seen a lot of activity in the breakout sessions, in all the chat series, in the presentation rooms, and that really superseded our expectations. And we are really glad, and we hope that that has really contributed to your experience of this conference. However, having said that, we also really would have liked to meet you in person here in Eindhoven, and that is unfortunately now impossible. But to compensate a little bit for that, we plan to host a smaller event next year, which we'll call Digital Concrete 2020 Revisited. It will be a multi-day workshop here in Eindhoven, and it's really about the focus on interaction and communication and building this young community, which is growing and growing very quickly. The situation with the corona crisis, unfortunately, is still that it is rather difficult to predict how well we will be able to travel in the near future, but maybe even into 2021. We have to see how it will develop. For now, I can only say keep an eye on our website and this developments, and obviously we will also keep you posted when we plan anything. Okay, now we have the practical notifications out of the way, and now we can proceed to the conference award. So the awards, they are bestowed by the scientific committee on the advice of the award jury, and therefore joining us now from the side of his swimming pool at his house in the south of La Douce, France, Nicolas Roussel. Nicolas, are you there?
Yes, I'm here.
Good.
Can you hear?
Yes, I can hear you. How are you
Good.
doing?
Oh, as you can see, I'm doing totally fine. I received many messages asking me about the pool since the opening session, so I decided that I will do the closing close to the pool. I asked for your authorization, and you very kindly authorized me to do so. So
absolutely,
here I am.
We hope to see you jump in at the end, maybe.
I could. It's just behind me.
Hey, did you enjoy the conference?
Well, my friend here, the Unicorn Balloon, and myself, we really enjoyed the conference. And my father used to tell me that in life you always have to choose between good things. You can't have everything. And the last 4 days, I had the feeling that I could be close to the pool, have fun, and then have my daily dose of science and very nice discussions, very nice information. So that was a very nice moment, really.
Wonderful. Well, I'm glad you enjoyed it. So maybe, shall we get to the announcement of the awards?
Yes, sure.
I give the word to you.
Okay. So first, maybe a few words about the way these awards were given. We had some preliminary work before the conference looking at the proceedings. And to do this, we selected among the RILEM technical committee members some experts in various fields. I have put the list here, and I would like to thank them very much because a conference is always a tough time, a lot of work, a lot of things to discuss and to see. But in addition, these people had to go through many papers and had to watch some very interesting conferences, lectures, yes, for sure. But some they did not choose because we were asking them to do so. So I would really like to thank them. It was quite tough because when we had to vote, well, not many potential awardees did not get any vote at all, so votes were quite spread. But we managed to identify what we thought were the best poster, the 3 best presentations, and the 3 best papers from the proceedings. So I'm going to move right now to the first award for the best poster. And after looking at all these posters, we decided that for us, the best poster this year for this edition would be, can we move to the next slide? Yes, thanks. A practical approach to assess buildability of 3D printed object using finite element analysis by Ab van den Bos and Pim van der Aa. So I really enjoy this poster. It shows how computational simulations can really help into designing process and objects. There's a very nice comparison between experimental results and numerical simulation. And good news, this is some industry people, so I'm really happy that this first award goes to industry, and they are from Netherlands. So congratulations to them. Myself and the unicorn, we're going to clap, because of course that's the part that we're missing in an online conference. We can move on now to the best presentations award. So there's no ranking. I'm going to list the 3 presentations that were selected, but well, we had a tough time too for this. Oh, I'm sorry, a plane is just flying above me. So we can move to the first one. And the first one is studying the bond properties of vertical integrated short reinforcement in the shotcrete 3D printing process by the group of Dirk Loek in Braunschweig Technical University, a very active and large group in Germany. A very nice piece of work dealing with a very important topic, which is reinforcement. Our second best presentation, oh, so forth, congratulations to them. And our second best presentations award, so of course I'm a bit happy about this one, a bit more happier than the others. It's characterization of the layer pressing strategy for concrete 3D printing by Paul Carnot, a PhD student from the Navier Laboratory in France. And this study deals with a way to print that consists into pressing the nozzle against the layer that you're depositing, allowing you for an amazing freedom in terms of shape and filament geometry. So congratulations to Paul. I think this is an award that is fully deserved, but like all the other awards here. And now we move to the third Best Presentations Award, which is a local one, bending and pull-out test on a novel screw type reinforcement for extrusion-based 3D printed concrete by Lorias and Frick Boss. So a very nice presentation. I mean, this one had quite some fans. And from TU Eindhoven, of course, we all know Frick now, and we now know Lorias from the Netherlands. And once again, a topic on reinforcement, which seems to be, I think, in this conference, something that is really moving well. So now we're going to move to the Best Paper Awards. So these were selected from the proceedings. After a first pre-selection process, we had a voting phase. And the final awardees are, without ranking, again in this case, application of 3D printed segments designed by topology optimization analysis to practical scale pre-stressed pedestrian bridge. I really suggest that you have a look at this paper. It's extremely complete. It goes from every stage. Of course, I'm sure that these people have gone into more details when they did the study, but they really present many, many things of interest at every stage of the conception and design. And this is one of our industry friends from Taisei Corporation in Japan. Our second Best Paper Award is Gravity-Driven Test to Assess Mechanical Properties of Printable Cement-Based Material at Fresh States from a French group in Brittany, South Brittany University. And this paper deals with new techniques to characterize the rheological properties of printable materials. I think it's a very nice exploratory work that gives some fresh ideas on the topic that are very different from the traditional rheometry we know, and that I think make a very good first steps towards some characterization tools that are very suitable for the materials we are looking at. So congratulations to Arno and his friends and colleagues. And the last, but not least, Best Paper Award goes to Influence of Processing Parameters on the Layer Geometry in 3D Concrete Printing, Experiments and Modeling from TU Denmark, Technical University Denmark, and DTI. and it's a very nice study that compares experiments and modeling at the level of a layer geometry, the cross section of the layer. So a topic I really enjoy myself, and I'm really happy that Raphael, Jan Spangenberg, and his colleagues got this award. So congratulations to them, and this group is from Denmark. So congratulations to everyone. Of course, that would have been better to be able to clap, to take a few pictures. Maybe we can catch up with this when we meet in real life in Eindhoven next year, but that will be a bit late. So we will send all the award documents and all the nice official certificates by mail to all of you, because I think that's something that you don't want to wait for so many months. So congratulations to everyone, and once again, thanks to all the jury members for this additional work that they had to carry.
Well, thank you very much, Nicola. And also from my side and the side here of the organization, congratulations to all the winners. And yeah, no big audience to applaud, but I'll do my best anyway. Yeah, for those of you who didn't win, there's always next time. Speaking of which,
for sure.
Nicolas, what about the next time?
Oh yes, next time. So there is in RILEM some general frame for organizing this type of conferences that belong to a series. So we have an open call for people to submit their proposal to organize, and then the decision is taken by the RILEM technical committee dealing with the same topic. So here, as the topic was new, we had a special procedure to start with, and we had to decide about the first two conferences, so Zurich and Eindhoven. Later on, we moved to decide about Loughborough. That will be the next conference, so in the UK. And what I would like to stress before we move to the presentation of this next event that will be very important for our community, I would like to stress that the call for DC, what would be DC 2024, is fully opened. We already had a few applications, but if you want to apply for organizing such an event, but I'm sure that Freek will tell you that it's a lot of work, and it is for sure. But I think it's as well a very strong satisfaction, and I think that we saw these days the work of TU Eindhoven, and I mean, it's a very nice way to visit some colleagues and see what they do. So this call is open for 2024, but for 2022, and we'll meet, I hope, in real life, and we can have what we miss the most here, which is the drinks, probably, and the nice food and a nice discussion around the table. But next time that will be in Loughborough, and now I will let my friend and colleague Richard Buswell tell us about this next event.
Well, that sounds wonderful, Nicolas. So, well, let's see if we can get Professor Richard Buswell on the line then.
Hello.
Hi,
Hey,
Richard.
how you doing?
So, we've just heard that the next party is at your place.
Really?
Yeah.
Oh, no, it's okay. No, it's all good. Yes, indeed. Yes.
Tell us all about it.
Okay. If I slide, can you see the presentation? First slide?
Yep. Super.
Okay, great. Well, it really is a great honor and a pleasure to host the third International RILEM Conference on Digital Fabrication, which in 2022 will come to Loughborough University. So Loughborough University prides itself in being a community-led campus which helps staff and students achieve their best in all aspects of learning, teaching, research and enterprise. As an institution, it has its roots as an engineering technical institute that's a bit over 100 years old. And the philosophy that it had then is the same now, which is sort of learning by doing, and a healthy body equals a healthy mind. Ooh, excuse me. So Loughborough is the largest single UK campus in the UK, and it's known for sport and engineering. So while Nicolas is topping up his tan, many people at the campus are trying to do the 100 meters in less than a minute. The university is home to about 17 to 19,000 students, and we support all sorts of national sports teams in rugby, cricket, tennis, badminton, and many more. We host a whole number of UK squads and many stars. So among them, Lord Sebastian Coe, who championed the 2012 Olympic bid for London, when actually Loughborough University was the base for the UK team. As a university, we deliver programs across engineering disciplines, civil and building, and mechanical, electrical, manufacturing, materials, across arts, architecture and design, business, social and sports sciences. We're ranked the 5th best university in the UK, and we are first for student experience. So where is Loughborough? Well, it's a town of about 60,000 people, and actually home to the world's largest bell foundry that casts bells for cathedrals all over the world, including Great Paul, which is a 16-ton monster cast in 1881 that rings in St Paul's Cathedral in London. We're in the Midlands of the UK with easy international transport links. We're just over an hour by train from central London, and that train is a 10-minute walk from the Eurostar or a tube ride from Heathrow. And there are local international airports in the nearby cities of Nottingham and Birmingham. So Loughborough is the home of concrete printing, and the parts we've manufactured in the past that I'm sure you've seen in images, the bench and the doubly curved panel. But of course, there are lots more about us. There are beautiful woods and woodlands to walk through that would have once connected Loughborough with the stomping ground of Robin Hood in nearby Nottinghamshire. The Bradgate House Park was actually the birthplace of Lady Jane Grey, who was famously queen for just 9 days in 1554. And we're home to vibrant markets that date back to the 1300s. We have an annual fair that dates back to 1228. The River Soar and the Grand Union Canals are the central waterways of England, and they run through and around the town. And we have the UK's only double-track heritage railway that is still running, part of the old Great Central line that runs north to south in the country. And just an hour away, there's the limestone dales and gritstone edges of the Peak District that awaits your exploration for those who want to look a little bit further. So with that, from everyone at Rylam and at Loughborough, and we hope to see you there in person in 2022, where we will welcome you to what I'm sure will be another fantastic event.
Thanks very much, Richard. I'm really looking forward to it. And yeah, I can only say I hope to see you there, but actually I also hope to see you somewhere a bit sooner than that. So
Absolutely.
Thanks very much for showing us the best of Loughborough. Okay, in the opening session in the opening session on Monday, I've already mentioned this. A conference like this doesn't solidify out of thin air. Many people have contributed to the success of Digital Concrete 2020. First of all, so I've seen, look now if I can get my own presentation on the screen. I will wait for 1 second. The first group of people that I want to thank for this conference is the authors, the presenters, and the keynote and invited speakers. Thank you for your willingness to bring your work to this conference. Having content to share is, of course, the core of any academic conference, and it's the cornerstone of academic development. So really thank you for bringing this to our conference. And just some slides of us in contact with the presenters, keynote presenters and invited speakers, but of course there were 110 parallel presentations as well. So there is so much research work that is kind of combined and being presented here. Thank you very much for that. Another group that I would like to thank very much is, of course, our sponsors. We have BMX, Twente Additive Manufacturing, Sika, Bekar, BASF, and Dow. Not only does, of course, your support make the whole organization of a conference like this possible, I also think that by supporting a conference like this, you are showing your broader support to the development of the digital concrete fabrication community. So thank you very much for that. Then there's also thanks for our media partners at Cement and CPT, the local facility management here at TU Eindhoven, and our conference support. And also thanks for RILEM for enabling Digital Concrete 2020. We've had a very good collaboration. And of course, we also like to thank you, our audience, for being with us and being so active during the whole duration of this conference. And now I'm moving on to a very special thank you section, and that is the thank you to our team here at TU Eindhoven. Obviously, we cannot get everybody on the stage at the same time because, social distancing. But I would nevertheless, I will call them up in a moment to thank them personally. There's one part of our team that I would like to mention in particular, and that is our technical support. And that is Karsten Nefs, Laurie Haas, Dirk Bos, Timon de Groot, Naomi van Hierde, and Femke Hermans. Let's see how many we can get within the 1.5 meter. I think we can manage. You were our tech team, and so now actually for the first time during the whole conference, there's nobody behind the support. So now I'm getting slightly nervous. I hope everything will keep running automatically. But to the audience, I would like to say, this is the team here that made it all technically possible. You wouldn't believe the amount of work that goes into it. And the absolute commitment of this group to top-notch quality that is needed to get to this level of conferencing is absolutely amazing. And we have some behind-the-scene pictures, which maybe we'll show just later on. That gives it gives a little bit of an impression of what is really needed to get this show on the road. So take a look at that and get an idea. To all of you here on the stage, I would like to say you went well above and beyond the call of duty. Without your efforts, this really would not have been possible. So thank you so much for having a superb job and done a superb job. I just say, but okay, sounds hollow, but it's really from everybody here. Karsten Nefs, thank you very much. Dirk Bos, please come into the camera. Timon de Groot. And you can wave if you want. Naomi van Hierde, Femke Hermans, and Laurie Haas. And you really, thank you for making this all possible. Thank you very much. Then our team was even bigger than this, of course. So we have a couple of people more that I would also like to thank. Maybe first, I just caught a glimpse of our colleague Sandra Lucas. I don't know if she's still here, but if she is, we're getting her now. Okay, then maybe in the meantime, I'll just say, Rob, can you come up? Rob Wolf, thank you very much. Next, Zishan Ahmed. Thanks very much for your support. Then we found Sandra. Come here. Thanks very much for your support and congratulations on your baby.
Oh, thank you.
Stefan Chavez Figueiredo. I'm still struggling with your name, but I hope to get it right sometime. And then there's, I think, only Theo Soletta. Last but not least. Thanks very much, Theo. Okay. I didn't forget anybody, yeah? Otherwise I would feel really, really bad. Okay, with that, that's really all from us here at TU Eindhoven. My name is Freek Bos, and thank you for being here and being everywhere. And we'll see you around at the next event. Bye-bye.
Welcome at Eindhoven University of Technology.